Okay, so I want to have a discussion here about, I think, a really interesting interpretation of the mass on a spring problems that y'all have been reading about in the book and in the notes and listening to my lectures about. This is about bridge designs. So there's a big consideration related to that when it comes to designing bridges. So the point here is that this equation that we initially looked at, thinking about a mass on a spring, actually applies to a lot of other systems. So in particular, any system where there's some sort of an inertia, some sort of a resistance to acceleration. If you think about it, that's kind of what mass is, right? Mass is that which, when you apply a force, makes it not want to accelerate as fast, right? F equals ma. So anything that has such a resistance will create a term in your differential equation kind of like this. And then likewise, a system that has opposite forces proportional to displacement. In our mass on a spring example, when you push the mass up, right, when the spring is stretched in that direction, the spring pushes back or pulls back in this direction. So opposite direction proportional to displacement. Any system that has such a thing will create a term kind of like this, right? And then likewise, periodic external forces. Now, this external force here is literally sinusoidal, but periodic, more general, right? Still structurally kind of like this. And so solutions to this differential equation are, let's say, relevant, right? Suggestive of solutions to this kind of a system, any kind of a system like this. Okay, so what kind of systems are there that are like this? Well, there's a lot of them, right? And what I'm going to talk about today is a structure, for example, a bridge. And if you have a structure, so a bunch of pieces that all fit together and connected in different ways, there's different ways in which it can move. So for example, you might have, let's suppose you build a box. The box can kind of move that way, maybe, right? There's just some extent it can move like that. That same box can kind of wobble this way, or it could wobble that way. There's lots of different modes. In addition to twisting that way, it might twist this way. Lots of different modes and ways that it can move. And note, in all of those cases, there's an inertia. The structure has some mass, right? If you apply a force on it, it doesn't just immediately want to move. There's a springiness to it. When you have a structure, the more you twist it, the harder it is to twist it, right? So roughly proportional to how far you've twisted it is how much it's pushing back. And therefore the possibility that if there is some sort of a periodic external force, we might have a problem. Okay, so important to understand, for any structure, there's several such modes, right? And all of them are vulnerable to resonance in the same way that a mass on a spring is, because they're all modeled by, well, approximately anyway, the same differential equation. Okay. All right, so that's a really big point. I want to talk about what does this have to do with bridges? And we'll start by talking about the Tacoma Narrows Bridge. This used to be in Washington, 1940. A long time ago. I'm going to show you all a video here. This is on YouTube. I think we should be able to leave this in the recording here for fair use purposes, this being a class. But anyway, if not, you can YouTube it yourself. Tacoma Narrows Bridge collapse. There's a bunch of recordings up there. And so let me show you what that looks like. Here it is. And look at that. Now, I just think that's amazing. This is a bridge made out of metal and concrete. And look, I mean, I didn't know concrete could do that, right? Isn't that stunning? It looks like it's made out of rubber. So this is obviously not a good thing. In fact, the bridge did collapse So I'm going to go forward here to where the collapse happens. And apparently they cut away the camera right at the wrong point, but then they got it back on it just as it was in the process of collapsing. So the bridge was destroyed, right? And this is a jaw-dropping phenomenon, and very, very scary, of course, as well. Okay, so that having been noted, I bring this up in the context of a discussion on resonance, because people used to think that this was resonance, and the thinking on the subject has changed in recent years. The reading that I've done suggests that it might be something similar called aerostatic flutter. That's beyond the scope of this course, exactly how that works, but it's not such a terribly different thing. The point here is that the worry about resonance is certainly still there. Okay, so it's something you definitely have to worry about. Resonance can knock down bridges. So I want to talk about a case where resonance actually was the problem. And this is the Millennium Bridge. So this is an actual example of a resonance problem in a bridge. This was in London, the year 2000, thus the name Millennium. And on opening day of the bridge, they had to evacuate the bridge for worries that it might collapse. So now, why did this happen, right? Surely they knew that resonance was something to be worried about. And yeah, absolutely. They were well aware of the dangers of resonance. This was not done out of ignorance. They just didn't anticipate the right external periodic force. So again, going back up to our list here, any sort of a situation that has an inertia and an opposite force proportional to displacement, if a periodic external force that comes up with the exact same frequency as the natural frequency of the system, then again, you have a huge resonance problem. So the big question is, what are the periodic external forces that are actually going to be in play? And again, they just did not anticipate it correctly. So now this is a bit of a discussion to describe, but roughly speaking, it was the people walking on the bridge that were the problem. So let's start with, we have a diagram here, and let's think about, suppose you have a bridge that's oscillating side to side like this, some sort of a, kind of bouncing back and forth sideways. Well, what would happen? People walking on that bridge. Well, look, the people walking on the bridge have to maintain their balance, right? And if you're standing upright, if these are your legs, and you're standing upright, and the bridge moves out from under you, you fall down, right? So people, without really even consciously thinking about it, solve that problem by widening their stance. And so then when there's a little movement like that, well, you've got a wide foundation, and you're not going to fall. Okay. Okay, so wide stance, and then furthermore, you take your own steps kind of in sync with the oscillation, because it's just easier to keep track of what you're doing, right? If it's oscillating sort of like this, well, then maybe you step to your left when it goes to your left, and you step to your right when it goes to your right, and then you've got a little rhythm going, and it's easier to keep track and easier to keep your balance. Okay, so the horizontal oscillation, out of a desire to not fall over, people walk with the oscillation. And if you think about it, if everyone's walking with the oscillation, they are also walking with each other. And so what we have was people walking in sync. Thousands of people, each one weighing, 100, 200 pounds, right? So we have hundreds of thousands of pounds of people all walking in sync, all walking with their legs a little bit spread to the side, right? And as the bridge moves to the left, everyone all at the same time takes a step to the left. And so you have hundreds of thousands of pounds of force pushing, well, mostly down, but somewhat to the left. And then as the bridge goes to the right, you have hundreds of thousands of pounds, well, again, pushing mostly down, but somewhat to the right. And that's a very significant external periodic force. that reinforces that horizontal oscillation. So you can see we have this feedback system here, right? And there's a chicken egg question of, what started it all? Were the people walking in sync first, and that started the oscillations? Or perhaps was there just a little bit of an oscillation and that caused people to therefore walk in sync? It doesn't really matter in some sense. But the point is, this got started going, and the oscillation got more and more and more. And again, eventually they did have to evacuate the bridge. So on opening day evacuated, and then they had to spend months retrofitting the bridge. First figuring out what in the world just happened. Right? Where did this external force come from? They eventually figured it out, and then doing the retrofitting. Okay, so anyway, the big takeaway on this is how hard it is to anticipate all possible sources of resonance. What are all the external forces that might come up? What are all the different modes by which something can sort of vibrate, sort of oscillate? What are the natural frequencies in each of those modes? And then making sure that there aren't any external forces to sync up with that. Okay, I also think I want to reinforce again over here, really big point is that this differential equation, again, about a mass on a spring, is about way more than that. It's about a wide variety of systems, any sort of a system that has these three properties, which again, if you think about it, not that rare, right? Resistance to acceleration, tendency to push back proportional to displacement, and some sort of repetitive pattern creating a force. So very big issues to be worried about. Okay,